Hello everyone, welcome to your channel Sukh Academy EduWorld. Today we will solve next 15 questions of chemistry prelims exam of Geo-Scientist 2024. In this question they are asking that consider a solution of 50 gram of an enzyme dissolved in water to give 2 decimeter cube volume of a solution at 27 degrees Celsius. We have to find osmotic pressure and molar mass of solute, that is our enzyme, is provided, and R value is also here, and so we have to find osmotic pressure. 50 gram of enzyme, that is our solute. Clear? This is dissolved in water, okay, and 2 decimeter cube is volume of resulting solution. Temperature is 300 Kelvin. Convert 27 degree to Kelvin. And molar mass of solute, that is enzyme, is given 90,000 gram per mole. R value is given 0.083 decimeter cube bar per Kelvin per mole. Okay. So osmotic pressure. Osmotic pressure is pi is equal to pi is osmotic pressure. That is equal to CRT. Clear? This is osmotic pressure. Relation for the osmotic pressure, that is equal to CRT. C is concentration, R is gas constant, and C is concentration. Okay. That is equal to number of moles per volume of the solution. So we can replace it by N2 over V RT. Number of moles per volume of solution. Okay. Number of moles of solute, N2, we can calculate number of moles of solute, that is equal to mass over molar mass of solute. And solute is enzyme here. So replace value of N2 by mass of solute over molar mass of solute into volume R into T. So this is our final expression to find osmotic pressure. Now we have to fill the values here. Mass of the solute is given 50 gram. Value of R is 0.083 decimeter cube bar per Kelvin per mole, and temperature is 300 Kelvin. Mass of solute is 90,000 gram per mole. We have to focus on the units also. And volume of the solution is 2 decimeter cube. Clear? So in this case, decimeter cube will cancel each other. And this is mole inverse and Kelvin. And Kelvin inverse will cancel out each other. So we will left with 50 gram multiply 0.083 bar. We can also cancel gram with gram. Yeah. So this will be, ultimately we will left with only bar unit which is the unit of osmotic pressure, pi 90,000 multiplied 2. Okay, so solve it. We will left with this one. We will get this as a answer, but in the question the answer contains unit kilopascal. So now we have to convert bar to kilopascal, and 1 pascal is equal to 10 raised to power minus 5 bar. So ultimately what we have to do, we have to divide this quantity by 10 raised to power minus 5 to convert it into pascal. This is in pascal. Okay, to divide, now divide it by 1000 to convert it into kilopascal. So your final answer will be 0.691 kilopascal. This will be your final answer. Okay, 0.691. So B is the correct option in this question. Next question. Consider the following values of normal boiling point and molar boiling point elevation constants for some solvents. And there are two solvents they are providing. One is water and one is ethanol. We have to find that which one of the following solutions would result in the greatest boiling point elevation. Okay. So in this case, they are providing us two different salt. One is lithium chloride and one is magnesium chloride. First of all, we have to find that which salt can provide greatest boiling point elevation, and if we compare these two salts, obviously magnesium chloride will show greater interactions in the case of both solvents, because magnesium chloride contains magnesium 2 positive, and in the case of lithium chloride there is a lithium positive. Obviously it will involve in greater a large number of interactions. So obviously A and B option is incorrect here, and we have to pick C or D option in this case. So if we compare the magnesium chloride, the and concentration is same, 0.05 molar in each case, and if we compare magnesium chloride in different solvent, one is water and other is ethanol. In the case of ethanol, there is large value of molar boiling point elevation constant, and you know that boiling point elevation is equal to kbm. M is molarity of the solution and kb is boiling point elevation constant. Ultimately, boiling point elevation is directly proportional to elevation constant, and which has higher value of the boiling point elevation constant, that have higher boiling point elevation. So in this case, in the case of ethanol, greatest boiling point elevation will be found. So D is the correct option in this question. In the next question, when a non-volatile solute is dissolved in a volatile solvent, the depression in the freezing point is. Uh, in the case of depression in freezing point, that is equal to depression in freezing point constant and M is molality of the solution. Molality of solution. Okay, so the depression in the freezing point, that is delta TB, is directly proportional to molality of the solution. So in this question, the correct answer is B. In the 64th question, consider the following statements regarding Henry's law. The Henry's law constant depends on the nature of gas. That is correct. CO2 gas is more soluble than oxygen. For these two gases, they are providing us data regarding Henry law constant. And if we compare the Henry law constant value for these two cases, for the oxygen, there is large value of the Henry log constant, and Henry log constant, that is Kh, is inversely proportional to the solubility, and for the oxygen gas has higher value of the Henry log constant. It means that it has lesser solubility. So yes, CO2 is more soluble as compared to oxygen. So B statement is correct. Henry law constant doesn't depend on the nature of solvent. It depends on the nature of solvent. So third statement is incorrect. The Henry's law constant depends on the temperature. This is also correct. So ultimately first, second and fourth statement is correct. So correct option is C in this question. In the next question, the value of the Henry law constant of oxygen in water at 298 Kelvin is this. When its partial pressure is 20 kilopascal, the molar concentration of oxygen we have to find at the same temperature, that is 25 degrees Celsius or 298. So value of Henry constant is provided 8 into 10 raised to power 4 kilopascal kg per mole. Clear? Temperature is 298 Kelvin. Partial pressure is provided 20 kilopascal. We have to find molar concentration of oxygen. Clear? So in this case, molar concentration is ratio of partial pressure and Henry's constant. So C is equal to P over KH. So partial pressure is 20 kilopascal and value of Henry law constant is 8 into 10 raised to power 4 kilopascal kg per mole. We can cancel kilopascal. So we will left with 20 over 8 into 10 raised to power 4 per kg mole. Clear? You can solve it. You will find 0.00025 per kg mole. And 1 decimeter cube is equal to 1 kg. It means 1 per kg is equal to per decimeter cube mole. Clear? And in the question, they are giving it answer in the millimole. So you can convert it mole to millimole. So you will left with this as a final answer, that is 0.25 per decimeter cube millimole. So convert it into millimole because 1 mole is equal to 1000 millimole. So you can convert this value by using this. Okay. So this will be your final answer, that is 0.25. So B is the correct answer in this question. In the next question, a conductivity cell was calibrated using 0.1 molar KCl solution and the measure resistance was 100 ohm. The resistance of the same cell when filled with 0.02 molar KCl is 500 ohm. The molar conductivity of 0.02 molar KCl we have to find. The conductivity of 0.1 molar KCl is provided, that this is a specific conductivity. Okay, specific conductance. So in this case, we have to find molar conductivity of the solution. There is a one solution, that is 0.1 molar KCl, and for that value of R is resistance is 100 ohm and specific conductance is 1.3 Simon per meter, and there is one other solution, that is, for that value of resistance is 500 ohm and concentration is 0.02 molar, and for that we have to find molar conductivity. So molar conductance is specific conductance into 1000 divided by concentration. Okay. So first of all, we have to find specific conductance of this solution. Then we will fill this value here and we will calculate molar conductance. And this can be find from this solution. So specific conductance is equal to L upon RA. Okay, L upon RA. So A is the area of cross section, L is the length of tube, so R is resistance here. Before filling the values, you can convert this specific conductance into Siemens centimeter inverse. So for that you can divide it by 100 and your specific conductance value will be 0.013 Siemens per centimeter. Now this value we will use in this expression. Kappa is equal to LRA, L over RA. In this case, we will find value of L over A, that will be kappa into R. Clear? So value of kappa is 0.013 Siemens per centimeter and value of R is 100 ohm. So multiply this value and you will find 1.3 Siemens per centimeter ohm. Now this value of cell constant, that is L over A, we will use to find the specific conductance of this solution. Okay, and in now come into this side. So we have found the value of L over A, that is 1.3 Siemens per centimeter ohm. Okay, now kappa to find here specific conductance, that is L over RA. So fill the value here. L over A value is 1.3 Siemens per centimeter ohm, and in this case value of R is 500 ohm. Clear? So we will left with here, this will cancel out, 0.0026 Siemens per centimeter. So this is the value of the specific conductance for this solution, which is used for calibration. And now we will find the value of molar conductance of this side, that is kappa into 1000 over C, concentration. Okay, this is 0.0026 Siemens per centimeter multiply 1000 centimeter cube over liter divided by 0.02. बोलो I, that is 0. Now we will solve it and we will left with 130 Siemens centimeter square mole inverse as our final answer of, that is the value of molar conductance. Okay, 130 Siemens centimeter square per mole. So this will be your final answer of this question. In the next question, the molar conductivity is at infinite dilution for nitric acid, acetic acid and sodium nitrate are given. We have to find molar conductivity for sodium acetate. Okay. So what we have to do? We have to we know that acetic acid will react with the sodium nitrate and will give sodium acetate and nitric acid. And we have to find the molar conductivity at infinite dilution for sodium acetate. So we will add molar conductivity at infinite dilution for both the reactants and will subtract the value of nitric acid. Okay. So add value of acetic acid and sodium nitrate and subtract the value of molar conductivity at infinite dilution for nitric acid, and the value is 391. Okay, and for sodium nitrate is 121.5, and we have to subtract the value for nitric acid, that is 421.2. Okay, after calculating we will get 91.3 Simon centimeter square mole inverse as final answer. So B is the correct option in this question. In the 68th question, the correct order of molar conductance at infinite dilution of lithium chloride, sodium chloride and potassium chloride. And if we consider the uh, size of the cation, lithium, sodium and potassium, these are belongs to the first group, and with moving down the group the size increases, and so lithium has small size as compared to sodium, as compared to, as the atomic size increases hydration energy decreases. So as the atomic size increases hydration energy decreases. And hydration makes the cation heavier, so mobility will decrease. So with increase in hydration, mobility of the cation will decrease. So in the case of these three metals, in the case of these three ions, lithium has small size and it involve in hydration easily, and in this case hydration energy will be maximum. If maximum hydration, in that case mobility will decrease. So if we compare the mobility, if hydration energy is inversely proportional to mobility of ion, so if we compare the hydration energy, so in that case maximum hydration energy will be in the case of lithium positive, then sodium, then potassium. So this is the case of hydration energy, and mobility and hydration energy is inversely proportional to each other. And so lithium will show lesser mobility as compared to sodium and potassium. This is the mobility order. Okay, and as we know that molar conductivity at infinite dilution is directly proportional to ionic mobility. So molar conductivity at infinite dilution is directly proportional to ionic mobility. And sodium and potassium will show maximum ionic mobility. So potassium containing salt will have maximum molar conductivity as compared to NaCl, as compared to lithium chloride. So in this case, the correct answer is B. In the 69th question, consider the following statements regarding ionic molar conductivities. So in the first statement, with increasing dilution, the conductivity keep on increasing. This is a correct statement. As the dilution will increase, obviously conductivity will increase. So in the case of a second statement, with increasing dilution, the degree of ionization of weak electrolytes increases and mobility of ions will also increase. This is also correct statement. With increase and dilution, weak electrolytes can dissociate easily. So that's why mobility of the ion will also increase and conductivity will increase. So both the statement 1 and 2 are correct. So correct answer is A in this question. In the next question, consider the following statements regarding ionic molar conductivities. Okay, and these two statements are related to Walden's rule, and according to the Walden's rule, molar conductivity, product of the molar conductivity and viscosity is almost equal to constant for ions in different solutions, in different solvents. Okay, so in the first statement, the Walden rule holds good for tetramethylammoniamine and picratine, and these two ions are large. Okay, and Walden's rule holds good only for large ions, and this statement is correct. In the second case, the effective radii of tetramethylammoniamine and picratine in solvent are larger and very different from the crystallographic radii of the ions. This statement is incorrect. Because the Walden first case is Walden rule holds good for large ions only, and the smaller ions don't satisfactorily obey Walden's rule because they are highly solvated ions, and a solvated ions also carries along the solvent molecules as it moves, and with the result that effective radii of the ions will be larger than the crystallographic radii, but it holds only for the smaller ions, and in that case crystallographic radii will be different in each solvent. But in the case in the in second statement, they are provided as the tetramethyl ammoniamine and picratine. These are the large ions, and in the case of large ion, electric field due to ion itself is very small, and the amount of solvent held to the ion is very small. So large ions are less solvated as compared to the so larger ions are less solvated than smaller ions. So larger ions having effective radii is nearly the same in different solvents. So ultimately the second statement is incorrect for these two ions because these are large ions and less solvated, and their crystallographic radii is almost same in different solvents, and this statement is incorrect. So first statement is correct and second statement is false. So C is the correct answer in this question. In the next case, consider the following statements regarding movement of the ions. First is ionic mobility is inversely proportional to potential gradient. So ionic mobility is equal to speed of ion divided by potential gradient. Clear? So first case, ionic mobility is inversely proportional to potential gradient. This is correct statement. Ionic mobility is directly proportional to ionic speed or speed of ion. This is also correct statement. In the third case, transport number of the ion is inversely proportional to the ionic speed. Since the transport number is directly proportional to ionic mobility. Okay, and we know that in the previous two cases, ionic mobility is that is denoted by U is directly proportional to speed of ion. So ultimately, transport number will also be directly proportional to speed of ion. So in they are provided that transport number of ion is inversely proportional to ionic speed. So this is incorrect statement. Next question, sum of transport number of ions in solution is equal to 1. This is correct statement. Sum of transport numbers of cation plus anion is always equal to 1. So first, second and fourth statement is correct. So D is the correct option in this. The next question is the following graph shows the variation of the molar conductance with the concentration of the correct answer of this question is B, that is weak acid, and we had already done the similar question in Geo-Scientist 2023 exam, and this question is repeating in this case also. So correct answer is B. In the next question, consider the following graph showing the variation of molar conductance at with concentration. Okay, and in this graph, this line is for strong electrolytes and this is for weak electrolytes. Okay, and which one of the following statements is correct with respect to the above graph? And the correct answer in this question is B. Plot 1 can be extrapolated to obtain the molar conductance at infinite dilution at strong electrolytes. For the strong electrolytes, we can easily extrapolate the graph at concentration C is equal to 0. Okay, but in the case of weak electrolytes due to dilution, however, degree of dissociation increases, number of ions increases. So lambda m, that is molar conductivity, will also increases but steeply on the dilution. Will lambda m increase steeply on dilution? Okay, near low concentration. So lambda m can't be extrapolated at zero concentrations for weak electrolytes. Okay, at infinite dilution, weak electrolytes dissociates completely. At infinite dilution, alpha will be equal to 1 at infinite dilution for weak electrolytes. Okay, for weak electrolytes, but at such low concentration, conductivity of solution is so low so that we can't measure accurately. So we can extrapolate this graph at zero concentration only for the strong electrolytes, not for weak electrolytes. So correct answer in this question is B. In the next question, the term A root C in Onsager equation, this represents the decrease in molar conductivity due to electrophoretic effect, decrease in molar conductivity due to asymmetric effect, increase in molar conductivity due to electrophoretic effect, increase in molar conductivity due to asymmetric effect. So the correct answer in this question is B, decrease in molar conductivity. The asymmetry effect includes the irregular distribution of ionic cloud around an ion in a solution. Okay, so when voltage is applied, finite relaxation time comes into play and leading to this asymmetry. And as a consequence of this effect, molar conductivity will decrease compared to the value when the concentration of electrolyte approaches zero. So that's why the dynamic asymmetric effect arises due to the formation of ionic atmosphere of the opposite charge around the ion. And this ionic atmosphere retards the motion of ion by including a force opposite to the direction of motion. So asymmetry effect, in the case of due to asymmetric effect, molar conductivity will decrease. Okay, however, if we consider the electrophoretic effect occurs due to the movement of solvent molecules attracted by the ion and the ionic atmosphere. And when applied potential is present, it tends to move the ionic atmosphere, which in turn reduces the ionic motion in the solution. So ultimately, the speed of ion and consequently molar conductivity are primarily determined by the frictional forces of the medium in the electrophoretic effect. So, the correct answer of this question is B, decrease in molar conductivity due to A. In the next question, the conductivity of 0.0101 molar dichloroacetic acid solution is this. This is specific conductivity. Okay. The molar conductivity at infinite dilution of HCl, NaCl, and this is given sodium dichloroacetate is given respectively. The degree of dissociation and dissociation constant we have to find for dichloroacetic acid. Okay, degree of dissociation, that is alpha, and dissociation constant K. Okay, we have to find. So ultimately, the value of a specific constant, specific conductance, that is 3.88 10 raised to power minus 5 Simon per centimeter. Okay, and the concentration of dichloroacetic acid is 0.001 molar, and molar conductivity of HCl is given, that is 426 Simon centimeter square mole inverse. Molar conductivity for NaCl is 126 Simon centimeter square mole inverse, and molar conductivity for dichloroacetic acid is 88 Simon centimeter square mole inverse, and we have to find lambda, alpha, that is degree of dissociation, and dissociation. We know that alpha is the ratio of lambda m and lambda m naught. Okay, molar conductivity at any concentration and molar conductivity at infinite. And we know that reaction involved between dichloroacetic sodium acetate plus HCl, and we will get dichloroacetic acid plus NaCl. And to find the molar conductivity at infinite dilution for dichloroacetic acid, we can find it by adding molar conductivity of dichlorosodium acetate plus HCl, and we will subtract the value of NaCl. Okay. The sodium salt For the sodium salt of dichloroacetic acid, value of molar conductivity is 88, and for HCl this is 426, and for NaCl it is 126. After calculating we will get value that is 388 Simon centimeter square mole inverse. So we have found the value of molar conductivity for dichloroacetic acid at infinite dilution. Now we will find the molar conductivity at particular concentration. Okay, so then we can find the alpha value. So molar conductivity, its unit is a Simon centimeter square mole inverse, that is equal to kappa Simon per centimeter multiply volume 1000, that is centimeter cube per liter, divided by molarity molarity which is in mole per liter. Okay, and the value of kappa that is already provided in the equation question, that is 3.88 into 10 raised to power minus 5 Simon per centimeter. Now fill this value into this equation number 1. So this will be 3.88 into 10 raised to power minus 5 Simon per centimeter multiply 1000 centimeter cube per liter divided by molarity is 0.001 mole per liter. Okay, now we will solve it. 3.88 into 10 raised to power minus 5 plus 3 over 0.001, and our overall units we can take here Simon per centimeter, centimeter cube, mole, liter, liter. Okay, this will be cancelled out. So we will left with 38.8 Simon centimeter square mole inverse. Now we have both value of molar conductivity at a particular concentration and at infinite dilution. Now we can find value of dissociation constant, that will be lambda m over lambda m naught, which is 38.8 divided by 388, and this will be 0. Now since this is a dichloroacetic acid, we know that if we will consider the case of acetic acid, this is a weak acid, but in this case there are two chlorine also, so in compared to acetic acid this is a strong acid. Okay, and for this case it will dissociate into plus H positive. Okay, and if its concentration is C, its concentration is 0 at initially, and after particular time after dissociation its concentration will be C minus C alpha, and here will be C alpha and C alpha. Okay, and dissociation constant is concentration of products over concentration of reactant. This is C square alpha square, we can take C common here, and here will be Kd is C alpha square over 1 minus alpha. Now we can find dissociation constant Kd just by putting the values here, just by filling the values here, and if concentration is 0.001 and value of alpha is 0.1 square, 1 minus 0.1, and after solving we'll get 1.1 into 10 raised to power minus 5. This is the dissociation constant, which is final answer. And if we consider options, the correct option will be This is the value of a degree of dissociation, and this is the value of a dissociation constant, that is Kd. So correct answer is D in this question. So remaining questions we will discuss in the subscribe, and don't forget to like, share and subscribe the channel. Okay. Thank you.